on a disk floating through space with a tiny sun.
Hey, I'm Fight the Flat Earth, and welcome back to the channel that lures stupidity into a windowless van. Tonight is a very special, dare I say it, monumental occasion, as we have with us a man who, by his own admission, has changed history. The one, the only Spurskimo. How are you feeling after today, Spurs?
Good evening, not too bad. How are you?
I'm doing pretty good. I watched your presentation earlier. I'm sure a lot of people in the chat also watched the presentation. People saying the audio's low, so I'll just make sure that's all up as
Good stuff, good stuff. Am I
Yeah.
coming through okay?
Yeah,
you hear me okay?
To me, and it should be all right. Okay, that's all the audio working. Yeah, so yeah, Spurs did a presentation earlier on Ranty's round table, where you basically disproved pressure, right?
Well, I mean, I would say so. I mean, the demonstrations kind of speak for themselves. We've been told there is a pressure of 14.7 psi. It's never been measured, it's never been calculated correctly. The tools, the devices cannot show this pressure reading. And, you know, the only real world pressure that we can actually measure with these tools are underwater, with water. And yeah, that's what I was highlighting today.
Right. Oh, that's amazing. I just want to say quickly thank you to Aussie Globehead. $50. I've already lost brain cells thinking about what Skidmark will say. Ask him if this 110011100001 will win me the Nobel Prize. Do you understand binary, Spurs?
I'm not a computer, so no.
Spurs doesn't understand binary, sorry. Right, just before we get going on your video, Spurs, it's another monumental occasion at the moment because we're celebrating the 50th anniversary of the Apollo 11 landings on the moon. Obviously, you're of the contention that they never went to the moon. What do you think that the astronauts were doing at this point 50 years ago? Because it was, I don't know, about 12 hours ago, 50 years ago, that they actually launched. So we would say that they were on the way to the moon. What do you think they were doing?
Yeah, I mean, again, because this is definitely a need-to-know basis. So obviously the astronauts would have trained, they would have truly believed they were going to the moon, right up until the point of actually going to the moon. So, and that's one of the reasons why I think they look so devastated in their interviews. But yeah, before that, so what would have happened to them is they went through the training, of course, that would have been for publicity, propaganda-wise, going through the various interviews and all those types of things. And, you know, and then as they approach the rocket, so to speak, they just go in one door and out the other, so to speak. And then they're given an explanation of, you know, this cannot happen. This is only done for, you know, the story is to beat the Russians or whatever. And then they get told the full story of why they can't go and what is happening and where they really live. Yeah, absolutely.
So you don't even think they got in the rocket and took off?
No.
So
in those days, there was no way they would... I mean, because they tested Neil Armstrong, he killed himself in the lunar lander experiment on Earth. So, you know, these types of things were not prepared. They were not ready to go to the moon of any kind. So, yeah, there's no way they would have put a man in a rocket to fly to the moon in those days. Yeah, absolutely no way.
Right. Okay. So so you just don't think they had the technology to even get people in a rocket and take off?
The technology. Well, the problem is that when you go higher, and this is where my video alludes to, or what it alludes to, as you go higher, the temperature drops so rapidly that the instruments the exterior of the rocket will just collapse and they'll malfunction, and they'd be unable to maintain the temperature of the rocket, the exterior of the rocket. It would just collapse. Yeah, there's just no way they could do it.
Okay. Super chat from Hunter Genrick, $5. What about pressure gradient in water? Scuba divers have to equalize their ears the deeper they go. Equipment starts to pinch as they go deeper. I don't think Spurs is disputing the fact that there is a pressure gradient in water, are you?
No, that's real world pressure. Yeah, so of course there's a gradient. Yeah, absolutely, underwater. Yeah, that's real world measurements of water. This is a real. Yeah, this is absolutely real. Absolutely.
Right. So one of the main things you've been saying is obviously it's not pressure, it's temperature. So does the temperature just keep decreasing the higher you go?
The temperature.
Yeah.
Well, this is the question. We haven't been able to get up high enough to know this. This is one of the problems. We get so high, our devices freeze and we fall back down. And, you know, this is another reason why things fall, things rise. Now, again, you'll have to think with me on this a moment. So if you were able to produce enough heat without combusting, okay, and your direction would be straight up. Or in fact, if you could control that direction, obviously you could go, but initially the heat would make you rise, right? So in my video, if you want to get the video up.
Yeah. Just one quick question before we do play the video. I'm just interested about the temperature. Do you think that there's a point where the temperature stops, or what happens when you get to the point?
Yeah, I'd like to know
this.
Yeah, well, this is it. But look, it's going to. If you want. Now remember, these things I haven't tested. I haven't been there. I haven't seen myself. So I can only give you what I would suppose would be the next logical step. Yeah. So it's not like I know this for a fact, right? But I can give you the logic of what we know. So you go above a mountain. It's very cold. You go even higher than that. It gets even colder. But now you're asking what's beyond that, right?
Yeah, we say obviously there's a pressure gradient, and the logical conclusion of that is that there's a point where the pressure is zero and you're in a vacuum, or near as damn it. Whereas you're saying that it is a reduction in temperature the higher you go. So I would just be interested to know what happens when you get to the point where the temperature was 0 Kelvin, because that's an absolute the same as vacuum. It's an absolute. There's an absolute temperature.
Yeah, I understand. I understand. Yeah, I understand that.
So I just wondered if you had an idea as to, does it extend past?
No, we can only go to
Kelvin?
assertions, Craig. I can only assert and suppose. Now, again, because it's not a container, right? Okay. And it's not gravity. So in my mind, I'm saying in your mind it's gravity. That's what stops the particles from going off into space. Yeah. Right, they get pushed back down. So, in this understanding, the particles, they go up, they get cold, they go cold, they fall back down, not because of a force, but because of the temperature is too cold for them to go any higher. And so, what's above that? This is the key. This is why rockets are trying to get beyond that, right? To see, well, what is there. This is what exploration is trying to achieve. You see, because we don't know. What,
do you have a point? Do you do you have an idea of how high you think we've been? Or
as high as the highest balloons or rockets that we see visually. The rockets that we see visually, that's as high as we can go. We don't see them go into outer space, do we? So we know they can't go that high.
Okay. $2 from Craig Connors. There is no way he actually believes this shit. It's a subject of contention as to whether Spurs is a Poe or not. He says no. Many people say yes. But let's have a look at the video that Spurs made. Now, one thing I want to say, Spurs, is that as Flat Earthers videos go, this was a pretty good one in the sense that the editing wasn't bad. The production values were pretty good. It was easy enough to watch. I disagree with pretty much everything that was said, but let's just have a listen to what was said.
But the part I'd like you to just look at for a moment, and this is where we can talk about pressure if you want, or temperature. Go to the last part, right at the end, right towards the end. I should have included more illustrations from it. I can't remember what the name of that video is, but if you could find it, that's a very good
see what it
video.
says.
Let's just turn
Okay,
that
it's right
down.
towards the end where he has the temperature, the heat coming from his. So go towards the end there.
Is this far enough?
Yes, around here. This is good. So look, so I say here, you can see there is nothing pressing on him. So you have to bear in mind, you wouldn't see this usually. All of this, what do you call it? This stuff coming off him? What is this stuff?
It's heat.
But what is it? Is it a substance?
No, it's
all right,
atmospheric
play.
disturbance. Is
All right,
the
play
way
a minute. Play
okay.
a second.
I was just getting that in full screen for you. Play. Here we go.
Just a few seconds because it's not on for very long. So out of his mouth again. Just pause.
Okay.
Pause here. Yes. So again, now you may be confused because you'll probably think this is like on a cold day when you see this coming out of your mouth, right? This is just in a regular room where you wouldn't see this usually. So this hot air is what exactly? What is this stuff? Is this not the atmosphere that you're describing?
What you're seeing is atmospheric disturbance. The same as you would see. The same as you would see if it was a hot day and you looked out in your street and you could see down the road that there was like wavy lines coming off of the tarmac because the air is hotter and it's affecting the light that's coming through it. It's atmospheric disturbance because of
where's the
changes
where
in
is the atmosphere? Where is the atmosphere then?
The atmosphere is everywhere, Spurs. What do you mean, where is the atmosphere?
Yeah, but how can we see it like this? This guy was showing, he said to you, if you watch the whole video, go to the beginning of this, where he lights the match. Just a few seconds before.
Your question there, how are we seeing that?
No, I know how we see it. I'm saying go to the beginning of it and listen to what he says.
All right.
Okay, yeah? So just back, here, start from there.
Okie dokie.
And just play this. Yeah, and listen to what he says.
Play, come on.
And this can be demonstrated.
If there were a portal through which you could see all of the invisible air currents, temperature gradients, and differences in pressure and composition of air, then this is what it would look like. The heat rising off your head.
Okay, so yeah. You can just pause it for a second, yeah.
Okay.
So you can see that he's saying that this portal is showing you the atmosphere. So all of what you're saying is supposed to be pushing down on him is the reverse here. We're seeing this stuff going away from his face. Nothing is pushing on him.
Wait.
Now you're saying there is something pushing on, and where is it? We can't see this pressing, right?
Right. So you think that his face is pushing the atmosphere away? Can I just clarify that that's what you think?
No, I'm asking you about the particles leaving his face.
Right. What's leaving
the stuff that's leaving his mouth is the same that he's breathing in. The stuff that's leaving his mouth, he breathes that in. And I'm saying that is the atmosphere. That's what he breathes out is the atmosphere. He breathes it in, he breathes it out. But you can't see that without this portal. That's my point.
Right. You do understand it's not an actual portal, right? So let me explain what's actually happening. What you're seeing is literally the differences in temperatures reflected in the wavelengths of light being distorted, so that you see certain, the heat that's coming away from him. As the heat energy is leaving his head, it is doing the same as if you looked at a hot road and you saw the wavy lines above it. That's all it is. You're seeing atmosphere distorting the light, the same as any other kind of atmospheric distortion. kind honestly a little confused as to what your point is here, because the atmosphere is all around him, and what you're seeing there is temperature differentials. That's all.
Exactly. Temperature, and the stuff that he's exhaling is the stuff that he inhales. The same stuff that he's blowing out, that is the atmosphere. That's what he's breathing in. You can see it there. He's showing you through a portal what it looks like. He said if you could see the different temperature gradients, he's included pressure because he's a pole earther. That's normal. But if you listen to it again, rewind and just listen to what he says.
I mean, I did notice that you cut out some. I'll quickly address the super chat. Area 85 restorations, $5 US. If Spurs doesn't believe air pressure is real, how does he explain multi-stage air compressors where the temperature is equalized between stages?
Where what? Pressure is equalized between stages. Who does that? Aeroplanes.
No, compressors. An air compressor, which literally compresses the air. Some of them work in multi-stages.
In a container. In a container. There's no problem here. But we're talking about in the real world, outside. So there is pressure. I'm not saying there is no gas pressure. There is such a thing as pressure, but not atmospheric pressure. So you need to really play. What you should have done, Craig, is just play the whole video from the beginning.
I was going
right,
to,
and
but
then
you asked me to go to the end.
Yeah, but you could just play the whole video if you want from the beginning.
Well, there's a few things that are near the beginning that I have questions about. Certain statements that you say.
Now you've got an audience here. You could just play it.
I'm playing it now.
You've given a little trailer anyway, so there's no
Hi, my name is
it.
Jody Gilbertson, and I go to Eagle Middle School. And my weather question is, why is it that high weather pressure is associated with fair winds and clear skies, but low pressure is associated with dark clouds and precipitation?
Great question. So we're talking high pressure and low pressure. She's saying, why is high pressure associated with clear skies and light winds, and low pressure associated with storms and rain? Well, we're going to put it together this way. You have to look at weather as three-dimensional. That's the key here.
Just little tip next time. Music's a tad loud.
Yeah, that's one of the most difficult. They started talking about the weather in 3 dimensions. I was so used to just staring at weather maps that I'd see in the newspaper here. Down at the ground, but everything at the ground is occurring by what's happening aloft here. So let's look at the gesturing. This is the gesturing here, and this is high and low pressure here.
I am going to show that atmospheric pressure is a complete hoax. And it's just another number that does not apply to the real world. Just like the assumed speed of light.
Right. That straight away kind of got me. Assumed speed of light. Do you honestly not believe that we've been able to measure the speed of light?
Yeah, but he says, again, this is why I included this video, because he says that he asked, the professors, and they said it changed between 1920 odd and whatever. So, it's not been a constant. It changes. It's just an assumed constant. So that's what he was saying. That's why I included it. Right?
Yeah. You understand that measurements get better as technology improves, and whenever the speed of light is measured now, with whatever device or any way of being able to measure it, it always comes up as the constant that we know it to be. Measuring the speed
would you
of
be able
light,
to demonstrate that?
it's very easy to demonstrate the speed of light. All you need to do is have a mirror at a known distance and calculate the time that the light takes to come back to you. I mean, calculating the speed of light, which is 180,000 miles per second, or 300,000 kilometers per second, which is bloody fast, but it's we can calculate and measure what the speed of light is, and there's plenty of things to do that.
No, that's just a theory. That's what they tell us, but we haven't really seen, an actual demonstration of a constant rate of the speed of light.
apart from all the measurements, you mean? That there is literally, what's the experiment? What's his name? The Fizeau-Foucault apparatus, which was literally developed to measure the speed of light. Beams of light directed at mirrors 8 kilometers apart. And it had like a rotating cogwheel in the middle. But this is one of the first times they actually managed to accurately measure it, and that it just surprised me that you would say assumed speed of light when there is so many easily found evidences that we know what the speed of light is. But anyway,
no, I mean, if you
that is definitely for another conversation. Let's move on with the actual crux of the video.
Okay. Very good.
But I want to spend a few moments on the constants of nature too, because these are again assumed to be constant. Things like the gravitational constant, the speed of light, are called the fundamental constants. Are they really constant?
The assumed shape and size of the Earth.
Under the approximation that the Earth is a perfect sphere, we can relate the angle separating the pair to the total number of degrees in a circle.
Again, assumed size and shape of the Earth, when Cavendish and the Sicilian are just two experiments which can easily weigh the Earth. And he's saying it here. He's saying, oh well, if we calculate this, if this is that, then this is that. We don't know, because what I was trying to explain is if you're trying to put a protractor on a ball, when if it's wider in the middle than it is the top, a protractor wouldn't work. You can't have a circle on this type of a plate spheroid. So all of these calculations don't work anyway. Yes, it's an oblate spheroid, but it's practically a perfect sphere. That's one thing that you need to understand. And the oblate spheroid can be very, very minute. And for all intents and purposes, the Earth is a perfect sphere. You don't need to treat it as an oblate spheroid because all the calculations work because it's pretty much a sphere. Again, it's not an assumed thing. Just bear with me 1 sec. I'm just putting on slow mode on the chat. 20 seconds.
Getting hectic out there, is it?
Yeah. 20 seconds. There we go.
I find if I read the chat, I can't concentrate on what you're saying. And
yeah, I know. Okay, right. Yeah. So anyway, let's carry on because there is.
But I do read it from time to time.
Ratio
I
of
do
the ground
like to
distance
see
separating the pair and the total circumference of
some
the
very
Earth.
big questions.
The assumed distance to the sun.
Creating a triangle that looks like this.
Yeah, so you then say the assumed distance to the sun, and then show Eratosthenius' experiment of determining the distance to the sun.
If he could determine the angle
was fantastic as well.
He could solve this triangle and determine ES, the distance from the Earth to the sun.
The assumed rate at which things form.
2, 1. There you go.
And
so I hope you
we discussed this last time. Guys, check out my previous debate with Spurs.
They both hit the ground at the same time. 3, 2, 1. There you go. So I hope you predicted it correct. As you can see, they both hit the ground at the same time.
Okay, I want to do it in normal speed so you can appreciate how fast the feather actually falls. So here's feather in a vacuum, normal speed. 3, 2, 1.
Yeah, we discussed this last time and how they do hit the ground at the same time. You just have to take into account the fact that the feather is tumbling and it is the same time. I'll just address a couple of super chats quickly. Justin James Homan, $5. Bike tires in the heat, hot air balloons. Heat equals higher pressure, Spurskimo. And then, thank you very much. And then there was one more. Area 85 restorations, $5. If atmospheric pressure is not real, then what is the difference between it and a vacuum chamber? Spurs, I have fabricated pressure sensors. What the fuck, man? Yeah, these questions we'll get there. Let's just carry on with the video for now.
Hit the ground at the same time. Hit the ground at the same time.
And any other assumed constants are just that. All assumed numbers with zero evidence to back up their assertions. And with zero evidence of these constants, you have to ask,
Zero evidence that was.
How did they derive a constant pressure of 14.7 pounds per square inch of atmospheric pressure?
Right.
Now, why that is interesting to know is...
Let's just stop it there, because that one question, I need to ask you something, Spurs. Can you explain to me the function of a barometer?
So the idea about the idea is that the mercury is in a tube or a container, and the pressure would press on the open side of the mercury, causing the mercury in the tube to go up. That's the idea, but whether that in practice that doesn't work, because when you take the mercury up a higher altitude, well, mercury contracts under cold temperatures, and which I put in the video also, and therefore if the mercury contracts, it freezes, becomes solid. Obviously, there's more, you know, it would malfunction. It wouldn't be able to take any readings. It would have to be recalibrated, so on and so forth. So it's not actually taking any pressure readings. It's actually taking temp.
So what is pushing on the mercury to register at sea level 14.7 psi? Why is the
There's no push. There's no push. There's a temperature, because this barometer doesn't give the same reading all over the plane, because let's say, for example, at Salton Sea, where it's 200 foot below sea level, right? This is on land, not underwater. 200 foot below sea level, the barometers should give a higher reading of 14.7 at least. And, you know, again, these things are not demonstrated. There are many places on Earth that are below sea level that don't give this reading, okay? That would give all kinds of malfunction, confused readings. And, you know, the higher you go, the colder it gets. So the only thing that affects the mercury is the temperature.
Quick question from the chat. Stringer News 1, $10. If temperature is a function of altitude, why don't we burn our feet on the ground?
Why don't we burn our feet on the ground? What does it mean? So you can burn your feet on the ground if you look again. You should play the video where go to the video. I don't know if you'll find it somewhere, but somebody cooks an egg on the ground.
Yes, yeah.
And how
we know that can happen.
Right, exactly. So if you were to walk on that surface, what do you think would happen? You would cook your feet.
Yes,
right?
I think he was being facetious. Do you know how much energy the Earth receives from the sun every hour?
No, I don't.
430 quintillion joules. That's why the ground
again, you know, you and your measurements. Again, I mean, I'd have to ask you, how do you know these things? How? Because remember,
you can easily calculate that by you can literally easily calculate how much energy the sun puts onto the Earth by leaving a glass of water in direct sunlight for an hour and measuring the temperature change in that water and the surface area and volume of the amount of water in there. And you can calculate how much energy has been imparted onto that glass of water. And then from that, you can extrapolate how much energy has been imparted onto the entire planet. So, you know, these kind of things are quite easy to do. But
no, it's not. It's not as simple as what you're making out, because the sun is not a hairdryer. It's not blowing radiation out like that in that manner where there's a pressure applied. You know, like a hairdryer with heat.
Oh, well,
it doesn't work.
There
like
absolutely
that.
is a pressure from solar radiation. We know that. But
no, it doesn't work like. This is the key. This is what we're saying here. This is how you guys have it in your mind. Like you think the sun is a hairdryer, Craig. It's not.
No, I don't think the sun is a hairdryer. I think it's a massive ball of nuclear fusion, a nearly perfect sphere of plasma, 93 million miles.
It doesn't act like a hairdryer, though. It doesn't act like a hairdryer.
In so much as the byproducts of nuclear fusion are expelled from the sun, including gamma rays and a lot of other stuff. So, in effect, it is blowing stuff out, but only in as much as the remnants of nuclear fusion. But I do have a very important question, Simon Dan. I was going to get to that. That was where I was going with all of this. So your contention is that the differences in a barometric meter reading are due to temperature change, right? So if I took if I had a barometer at the bottom of the Himalayas...
No. I'm saying that the temperature affects the mercury in the barometer.
Yeah.
So if you take this barometer, so usually people have them at home, but the temperature is warm, it's ambient.
All right.
But if you took this device,
let me ask my question then. So so you're saying that it is the temperature change that will affect the reading of the barometer. So if I at the bottom of the Himalayas and I read it at 14.7 psi, and then as I rose in altitude, the psi would drop. You're saying that's because there's a temperature drop, right?
Yeah. So
okay. So my question with that, and it's a very important question, is why is there the same barometric reading at sea level in the Sahara Desert and Antarctica when there's a temperature differential of up to 60 or maybe 70 degrees?
Right. They have to be calibrated because the
barometer... I could take the same barometer and read it in the sea level in the Sahara and sea level in Antarctica, and they will both read 14.7. It will read, the same barometer will read 14.7 psi.
That's not true. No, that's false information.
Do you have evidence that isn't the case? Because here is how I can prove that. I have been on a ship that has sailed from Antarctica up towards the Middle East, and the barometer on the ship was the same one. We didn't change barometers. We didn't calibrate it at different points. That barometer on our ship read 14.7 psi when we were right next to Antarctica and when we were right next to somewhere that's bloody hot. So there was a massive difference in temperature. But the only...
No, you're kind of begging the question, Craig.
No, I'm not begging the question. I am giving you direct observations that I can guarantee you millions of people at sea can also give you that direct observation, that a barometer will read the same when you're at sea level, no matter the temperature.
No, it won't. That's not true. Again, that's the misconception.
So I live in Scotland, all right, and trust me, the temperature here in Fife can literally change from like 20 degrees C to like 5 degrees C. So you're telling me that if I had a barometer...
I'm not going to tell you this, Craig. Play my video, right? The pilot, listen to the pilot. He says that when he's using his altimeter, these devices, that he has to calibrate them because it will tell them that he's higher than he actually is. If he goes to a different airport, he has to change everything because it tells him that they're at different heights. So I'm not saying that you don't know what you're talking about, but I've researched this and I've looked at what they've said, how they do it. Now look at what the pilot says about how he calibrates his altimeter.
Okay.
And what the computer thinks it is when it's not.
Right.
It's a little bit quick. Yeah. Play that.
You do know an altimeter is not a barometer, right?
Yeah, but these devices are all...
because the QNH obviously is different between the...
Yeah, let's have a look here.
Different airports. So, for example, today, the QNH here in Girona is 1,015 hectopascals. And I'm just about to start flying. We're going to fly to Baden-Baden in Germany. And the QNH there is going to be much lower. It's going to be 1,002 hectopascals. Okay. So, it's really important that we use the correct pressure setting at the airport we're at, because otherwise our altimeters is not going to show us where we are. Okay. If I, for example, sit here, the QNH 1,015, and then I wait for a few hours and the pressure drops, well then the altimeter will assume that I have climbed during that time, and it will show me, if it's dropped, for example, 3 hectopascals, well then it will show that I'm actually 90 feet higher than what I actually am. This is why it's so important that we continuously update the pressure setting when we are either departing from an airport or descending into an airport.
Once you...
Okay, so my main point with that is that it registers a difference in pressure.
Right, so all he spoke about was pressure, right? And he's saying that the pressure drops, but what he's really saying is that the temperature is constantly changing. Imagine at an airport, the temperature would constantly change. They have to wait to make sure that the calibrations can be done correctly. And then when they take off, they have to land with the calibrations made correctly. So, you've just heard it there. They have to constantly update because the machine doesn't know where it is. It thinks that it's higher than it actually is because of the pressure.
Because they're not a barometer. But
Spurs,
what you're missing is the main point is that it registers differences in pressure. Okay.
So listen to that. That's what I asked. If the pressure is 14.7 at sea level, and he's sitting there, and the pressure is 14.7, and he says the pressure drops, what does he mean? You explain that to me.
Say that again.
If he's sitting there and he talks about the pressure dropping, what does he mean by that? How can the pressure drop? What does that mean?
That means that there's a change in pressure. I'm confused by your question.
So if the pressure is 14.7,
yes,
is he saying that the pressure is now 12 point whatever or 10 point something?
No, he's not.
So what does he mean that the pressure has dropped?
Because it'd be at different altitudes.
He said he's sitting there and the pressure drops. He has to wait for all these changes. What pressure drop? What does he mean by that? Explain that to me.
This is all to do with the equipment on a plane and how it functions.
All right, rewind
and it doesn't
use
use a barometer. And you're dancing around the points that I'm making that ruin your whole argument. And I kind of want to ask you this again because that's the wrong one. It's quite a big point. Like you're saying that it's not pressure, it's temperature. But a barometer disproves that because it can be really warm inside my house, but less cold outside. And I can take that barometer from inside to outside. Wait, I can take that barometer from outside to inside, and it's not going to change in pressure. Yet the temperature is different.
Pressure drops. I want to know what it means by pressure drops. What does that mean? I don't understand what pressure drops means. Explain to me, Craig, what it means.
It means that the pressure would, in relation to what the pilot was saying, Spurs, is that the instruments on board have to be calibrated to where they are because that's how they function. But they are not a barometer. Now you're dancing around.
But I'm asking about
you're dancing around my question, and my question is very, very important, Spurs, and that is why does a barometer not change when I change the temperature? Why can I walk outside my house where there's a different temperature and the barometer not show me something different? You are saying
that will happen. That does happen. That will happen.
No. It really, no, it really doesn't. A barometer will not change when you move. I could put my barometer in my oven, and it would still read the same as outside of my oven. But if I put that barometer in my pressure cooker, it's going to read a lot higher.
That's not possible, Craig. That's not possible because the pressure would change in the oven.
Not so much as if I put it in a pressure cooker. All right, if I went from.
Doesn't matter.
If I like the difference in shade on a hot summer day, there can be like 10, 15 degrees difference in temperature between the shade and in the sunlight. So why does a barometer right next to each other, but one in the shade and one in the sunlight, not read different?
But you're saying it yourself. A barometer in a cooker has to change because the temperature means pressure.
Spurs, answer my question. Why does a barometer not change when there is a direct difference in temperature change?
It does change.
So,
of course it changes.
Right, so during the day, at solar noon, it's really bloody warm and then it gets colder during the night. Why does the barometer not change as the temperature changes throughout the day? Spurs,
it does. It will change.
Oh, tell me when that ever happens. That a barometer will read the same throughout the day. At sea level.
Yeah, so the guy just told you. He said the pressure dropped.
He wasn't talking about a barometer. I'm talking about a barometer. And we're going to stay on point. No, Spurs. He's talking about the function of aircraft instrumentation. He's not talking about a barometer. We are talking about a barometer. And
I'm not talking about his instrument.
Yeah, but
I'm not talking about the instrument.
I'm talking about a barometer. And that is the crux of the matter here.
So this barometer is still...
No, he doesn't have a
I don't think
barometer
you
on his
understand.
plane.
This
He doesn't
barometer
have.
is still...
Spurs, stop. He doesn't have a barometer on the plane. We don't need to worry about what he's talking about. We are talking about your assertion that there is no change in pressure, it is a change in temperature. If that is the case, why does a direct change in temperature not affect a barometer?
It does.
No, it doesn't. Why?
Well, you have to demonstrate that.
Okay, a barometer will measure 14.7 psi at midnight and midday. There's a difference in temperature, yet the
saying it doesn't make it true. Shouting doesn't make it true. There is no 14.7 in the first place. First of all, you have to demonstrate how you have this pressure.
No. Spurs. Right, you are going against what everybody knows about how what a barometer will show.
Yeah, absolutely. And I told you this is a rewriting history. This is groundbreaking, Craig.
You need to prove that a barometer will show different.
Craig, you should be glad that you're part of this, right?
Yeah, and
you're
I'm
here right now.
Spurs, I'm asking you for evidence, okay? And the evidence I require is proof that a barometer will change based on temperature alone. If that is the case, then I could take a barometer and put it in my freezer, and it will significantly change the reading.
Yes, right? Absolutely. Look, go to my video. Go to the video where it shows the demonstration for atmospheric pressure. Go to this. Let's have a look.
Where is
the same way a barometer
in the
near the end. Let's have a look here. This demonstrates. It's not a barometer, but it's the same principle that the guy when he first invented it, how he used it. Right. So let's have a look here. Get the video up and then we'll. So it's got the candle. So you're looking for a candle and an egg in a bottle, and the water or the
bottle.
Yeah, the liquid. So look for a red candle.
Oh right.
And
I remember that bit. That was quite funny.
Yeah. So this will explain how a barometer is supposed to work and how the readings are what's supposed to be happening. So have you found it?
I think this is the point. Let me just play it here.
Makes sense if there were really an actual force
forward here
on you.
You don't need sound. You can turn the sound down.
PSI pressure.
You don't need the sound. Yeah, go forward a little bit more. Forward. I can see it on the thick mini screen. Yeah, forward. On the mini screen, forward. Yeah, forward more. You may have gone past it, but keep going.
With the egg on the ground. I'm looking for the candle bit.
Yeah, no, so go back. So no, it's not in that area. Go back.
Is it all this?
No, back. So it should be around here. There we go. Right. So this
tell us what's
here.
happening, Spurs.
Yeah. So this to pause here.
Pause. Okay.
Oh, go back. Yeah. Not on this one. On the red candle. Same principle. Okay. Yeah. So we can talk through it as he's doing it. So pause. Let's have a look here.
Okay. Tell me what's happened, Spurs. Tell me why that liquid has gone into that tube.
Right. So this could be wax, water, mercury, any liquid, any type of solution that will, take a pressure reading, so-called pressure reading. So what's happened here is what we're told is that the outside pressure has pressed on the water on the plate and pushed it up into the cylinder there. Yeah?
Mm-hmm. Yeah.
But what's happened in reality is the flame, as I explained to you last time, created a vacuum by burning up all of the oxygen in that sealed chamber there, which causes suction, which sucked all of the liquid up. Now, now let's say, for example, we didn't have the flame, and go back a previous second, if you don't mind. Just
just a second or two. Just a few seconds. No, yeah, with the red candle.
Okay.
And
I'll just let it play from there.
Yeah, stop. Oh, okay. All right, just pause it. Yeah. So look, so as that's going, so what would happen if you take this plate up a mountain?
Good night, Sam and Dan.
This effect is supposed to happen, where the liquid would rise, and as you come back down back down the mountain, the liquid would do the reverse, right? But if you were to take this liquid to the top of a mountain and higher, it would freeze, and then you wouldn't be able to take any readings. So as you come down the mountain, it melts, it expands, right? And as it expands, it starts to push out of the cylinder and onto the plate. So it's very simple science, right? So there is no pressure force there. And if you play the video on, like I say, the egg is the same thing.
Okay, so right. First off, what's going on inside the tube? The oxygen isn't really getting used up. It's being bound to carbon during the combustion, and it goes to a point where it can't be used for combustion anymore. And what that does is it causes a temperature difference inside the tube, which creates a difference in pressure, which allows the air pressure outside to push the liquid into it to fill up the volume of space that is now gone during the combustion. So, as I explained to you before, there isn't a vacuum inside there. There isn't really a difference. All that you've done is you've changed the oxygen, so you can't really use it for combustion anymore. And that is changed the temperature and the volume of the gas, which has allowed the air pressure to push the liquid in.
Inside that chamber is very, very low temperatures. So the warm is rushing to fill the cold space because warm air rises. So, at the bottom, it's pushing up where it's warmer, and at the top where it's colder is, and that's why obviously it doesn't go all the way to the top. So if it were really atmospheric pressure, you wouldn't need to light the candle in the first place. That's the point.
Yeah, actually, that is exactly the opposite, because the lighting of the candle and then the oxygen, combusting and bonding to the carbons is all that's going on in there. You're not using up the oxygen. You're not taking away anything. It's mostly a change in temperature that creates the pressure differential that allows air pressure to push the liquid into it. There is no sucking.
Well, that's not.
The main thing, the vacuums don't suck, and that can be proven by the fact that someone made a massive straw, and there was literally a certain point that you couldn't suck the liquid up anymore, because there wasn't enough atmospheric pressure to push the liquid all the way up the massive straw. No matter how much you sucked, you couldn't ever do it. And then they attached an industrial kind of vacuum pump to it, and it still couldn't lift the liquid up any further than a certain point, because it's limited by the atmospheric pressure. So if the atmospheric pressure isn't strong enough to push up the certain weight of whatever liquid, then that means that you could never suck liquid all the way through a massive straw, because it is limited by the atmospheric pressure, which is proof that what's going on there is the pressure pushing the liquid into the tube, because vacuums don't suck. If they did, then you would be able to suck material up a straw no matter how big the straw was.
Yeah, but remember, the oxygen is warm, very warm, it's very high temperature compared to where it is now, where there is zero oxygen.
No, that's
not zero
true.
Oxygen.
The oxygen,
not zero oxygen. Yeah, but it's very, very low amounts of oxygen, which creates a very cold temperature. You see?
Okay, so yes, there's a difference in temperature. As the flame goes out, there's a difference in temperature, and that's the main difference, and that creates a pressure differential that that allows there to be less volume in there that then lets the air pressure push it in. But say that tube,
we know that.
Say that tube was 30 stories tall. No matter how much something sucked, you couldn't get it all the way in. Now,
because
I'm just gonna
warm air rises, right? So if there's a situation where there is cold air versus warm air, so that's why there has to be more cold above us than the warm air. You see, so otherwise, we would be cold everywhere. In fact, that's why it's cold at night, right? Because there's not enough light or sunlight to warm up everywhere. But the higher you go, the colder it gets. A vacuum just means very cold, extremely cold temperatures, and that's what that chamber is experiencing. And so the warm air or the warm air around the room is just being sucked up by the cold air. And again, this can be demonstrated with, you saw the egg. There was a young boy straight after that where his tongue was stuck to a pole, and that demonstrates again a vacuum because we have very low pressure.
Wait.
And what's happening? Look, go to the video. Go to it where the egg and then the boy afterwards. And this is easy to explain now. You see with the demonstration.
Right, one sec. Team Skeptic's coming in. He's got a couple of questions as well. I'm just going to quickly address a few super chats first before we get there. I don't know where we got to before. All right. Ask Spurs what the internal angles of a triangle are with sides 1, 1, and 1. Spurs, would you know that?
Look, we're not getting into...
Okay, all right. Anyway, that was $5 from Created Nothing. $5 more from Jeremy H. I bet Spurs brushes his teeth with crayons. Tasty. $1.99 from Monochromatic Light Source. How does a pressure cooker work? Pressure. $2 from Malicious Bloke. Digital barometers give same results as mercury. $5 from Curtis Reynolds. Pilots have to calibrate altimeters to the current barometric pressure. They're not calibrating the barometer. Yep. Thank you. $10 from Stringer News 1. Spurs, altimeters are set to the pressure altitude of the nearest airport. Why did you lie about what Mentor pilot said? $2 from Earth is seriously flat.
Hold on, let me address something here. Sorry, before you go.
Right. So I'll read that to you again. Stringer News 1. Spurs, altimeters are set to the pressure altitude of the nearest airport. Why did you lie about what Mentor pilot said?
No, not that one. About the, he says, the mercury is not calibrated to 14.7 psi. We know this. This is the point. So the mercury is whatever you want the number to be. This number of 14.7 psi is only found underwater.
Okay, right. $2 from Earth is seriously flat. Love is teaching children how to test D-Globe. Earth is seriously flat. I didn't quite get that. Could you do some more of those super chats? Maybe we can read them out again. $10 from Bearded Devil 1864. Conventional aircraft altimeters work by measuring atmospheric pressure at the airline pilot's flight altitude and comparing it to preset pressure valve. £5 from Dan Robinson. Asks Wank Steak how siphoning fluid from one container to another works without pressure. $2 from Earth is seriously flat. Thank you again. $2 from the Snark. Spurs, if you looked up the composition of air. $5 from Bearded Devil 1864. The outside atmosphere pushes the liquid to equalize the inner pressure of the unsealed glass after the oxygen was expanded. $5 again. The liquid will be suspended even after both temps have equalized. And $2 from Brian Green, FTFE, asking what 3 minus 1 is again. Right. Anyway, team, how are you?
Yo, what up?
All right.
Hello, everybody.
Welcome. How are you doing, sir?
Good evening, Team Skeptic. Good evening.
What up? I'm coming in late to it, and I was working on my video, so I was listening in on the, and yeah, I just figured I'd step in and catch the end of this. But are y'all shutting it down or something?
No. I was just reading. I'm trying to just stay on top of the super chats.
Okay.
Rather than having a long list.
Okay, good deal.
So you do you have any questions for Spurs about what he's saying about what's going on here with the candle?
Yeah, just one. Spurs, are you gonna have a problem if I make an idiot video about you?
No, I mean go for it. Whatever floats your boat.
Okay. Well, just don't take it personal.
Yeah, he
I actually
recognized
kind of like you as I kind of like having you on as a guest sometimes, but you know, I got to do my thing too and entertain the people. And I felt like that video you showed was very entertaining, to say the least.
Go for it.
All right. So, team, can you explain to Spurs what's going on with the candle here? Because he doesn't seem to be getting it from when I'm explaining.
Yeah. Okay, so gravity's pulling down on the air, which is pushing down on top of the water, which is pushing up into the glass, and when there is oxygen on the inside of the glass, you know, before the candle is burnt, then there's a pressure that's pushing down as well from the inside of that container. And that pressure is equal to the pressure on the outside that's pushing the water down as well. Because if it was greater, then it would push the water out of the way. But it doesn't. So it's in an equilibrium state. When he burns the candle, it takes it out of the equilibrium state because it removes part of the oxygen from the inside. Now what happens? It still wants to equalize. The only way for it to equalize at that point is to, you know, the water goes up the container and causes the air to condense again until the air it reaches a state of equilibrium on the inside from the outside of the container.
No, that's incorrect. So what's happening here, again, it's all to do with temperature. So what's happened is the oxygen has been dissolved, as we can see. So this is a very cold area. So what's happened is it's trying, like you talk about equalization, yes, but it's trying to find an equalization with the outside temperature and the rest of the candle, you see? So it has a problem. This cold area is not comfortable being around.
Can I address that? Can I address that real quick? Can I just real quick to address that? Okay, so the laws of thermodynamics say that eventually those temperatures are going to reach an equilibrium. When those temperatures reach an equilibrium, why does the candle not sink again?
Why doesn't it sink? Well, that's the point. There's no pressure there. There's no more temperature change. It's now at an equilibrium. There's no need. There's no force.
No, you
there.
said.
No,
hold on. You just said that the candle is pulled up because of temperature differences, right? Did you not just say that?
No, yeah. So the temperature above the.
Okay, so when the temperature equalizes back out, why does the candle not sink back down to its original state?
Because the temperature is the same now, everywhere.
You're contradicting yourself. You're saying you're saying that the candle is pulled up. Hold on, Spurs. Hold on. You're saying the candle is pulled up because of a temperature change, right? Yes or no?
Not the candle.
You're saying that they burn out all the oxygen on the inside.
The liquid.
Listen, you're saying that they. Okay, yeah, you know what I'm saying. Yeah, I'm talking about the liquid. I'm talking about, you see how the candle lifted up just there? That's what I was talking about. Yeah, the liquid,
so
okay?
Liquid, so listen,
you burn, you're saying that...
Pause on the egg. Pause on the egg one. Pause on the egg one. Pause the egg one. When the egg is going in and out. So the egg is a bit easier to understand because we can see it clearly. But the egg, right now, look, is being pulled in because you see when it was cold. Go back, Craig. Look, show here the temperature. This is a clear demonstration. The egg. And then pause when the bottle is cold. Look, pause. Right. So this cold temperature is freezing cold compared to the outside temperature and the egg. So this area where it was cold creates a pulling sensation because now the air is trying to equalize. Now, what happens when the egg goes inside, it can't be pulled back out. You can reverse this actually by creating the same thing, a vacuum again. That's the only way to get that egg back out is to create a cold temperature, very low temperature, and then it will be pulled back out. And that demonstrates it there perfectly. They showed you blue, cold temperature, and red for the hot temperatures. So I understand what you're saying.
Okay, well I've never seen that one before, but I'm asking you about the one because you were explaining to me how wrong I was about the candle, but I was trying to explain to you that I'm not wrong about that. Like
it's the same thing with the egg.
You were saying but what you're saying is contradicting yourself though. Okay, so what I'm telling you is that
it's not contradicting. It's like you're not listening to what I'm actually saying.
the air in the bottle has to equalize with the air outside, and the egg and the candle and everything around it. There's like it's like a contradiction. It's like, well, what's going on? Should I be warm? Should I be cold? What's going on? So it's trying to equalize the pressure. Once you remove the oxygen, you rapidly drop the temperature. Now there's a problem. It doesn't know which way to go, so it just gets pulled up. Nothing to do with any pressure here. It's to do with the temperature. So now once it equalizes, it's not going to move. It won't go up, it won't go down until there's a temperature drop or rise. Yes?
Okay,
That's
so
it.
what happens
Nothing-
if they pick up the glass? What happens if they pick up the glass? It falls, right? Everything on the inside of the glass falls if they pick it up, correct?
What do you mean?
No temperature has
What do you mean?
changed. If they pick that
What do you mean?
glass up off of that plate. No, hold on.
Well, you need to
When the
pause it
candle
on
is
something.
being
No, look,
shown.
you need to pause it on pause it. Ask him to pause it on. Pause it here.
Go to the.
Where? Look. Pause it somewhere, Craig,
Alright,
so we can
go
discuss,
back to the candle.
Yeah,
That's the candle.
pause. Right. So.
Okay, so when the cup is lifted up, okay, and the candle is with the red one, this one will work too. It doesn't matter. When that cup is lifted up, there are no temperature changes, but yet still everything will fall out of the cup. Why?
No, what do you mean there's no temperature change? As soon as
Yes.
the oxygen has been destroyed, the temperature drops.
Craig, will you go to
immediately.
this one right here? Okay, hold on. Play it here. This is that red candle that you were just at.
Yeah, it's gonna go to that after this bit, I think. Yeah, it's next.
Okay. So Spurs, you're
No,
saying
I can't do
that
this much
there's a
longer anyway. I
temperature
did say,
change.
Craig, I can't. So, team, we'll have to do this on your channel because there is much more to go over, and I don't want to fall out of you already over this discussion. So,
Go pause it. Go pause it. Go pause it right there. Hold on, Spurs. Well, I just want to ask you this question. I want to understand your position here. Okay. Pause it when that went right there. Pause it. Okay. So, you're saying it stays up there because of temperature differences. You're saying that there's pressure differences, that it equalizes at a lower temperature, and it just has no reason to move, right? Well, if they pull up that cup off of that plate, everything will fall down, even though there's no temperature differences, no nothing. Why?
all right, I'll give you another example. Craig, please go forward in the video. There's a better example of this. Go forward. Oh, it might be at the
Spurs,
beginning
you're
of
not
this,
answering
actually.
my question.
Yeah,
I'm going to answer it.
You're not answering my
It might be
question,
the-
though.
Just skim through the bottom, Craig, so I can see the thumbnail, and I'll tell you. Go back to the beginning of all
I'll
this.
look into that egg thing. I've never even
Go
heard of that,
back,
so
back,
I'll look
Craig,
into
back,
the egg thing.
Back, more back, look back. Here, go to this expert. Here, forward. Yeah, just after this, just after all of this. Right, look. Here again, another example, right, of what we're describing here, right? So look how strong vacuums actually are, right? So, same principle. What's happening here now is everything is being sucked up. And now he's creating a very cold vacuum.
No. Spurs. You're getting it wrong. Nothing's being sucked up. Here's what's happening. Air pressure pushes in all no matter which way he holds that plate. Air pressure is pushing with the same intensity in all directions. So he holds that plate up on the side, okay? Air pressure is pushing it sideways. There's nothing on the inside of the cup to push it back. If there was enough pressure on the inside of the cup to push it back, then the plate would fall.
Yeah, the only pressure that can be applied to that is he will apply the force. But go back, Craig.
No. He takes the he has when he puts that plate down there, when he puts the cup on top of the plate before, let's say, without igniting the fire, okay? When he does that, there's an equilibrium of pressure on the inside. Spurs, there's an equilibrium of pressure on the inside. Okay. All right. Well, it's going to be the same answer.
So I've got a question. The source that you got the egg video from, where is it? So this video that you got, where they're talking about what's going on, what did they say was in this video that you got the source from? What did they say?
They all say atmospheric pressure. All of them say atmospheric pressure.
So even the sources that you're using are trying to explain that it's atmospheric pressure.
Yes, but the thing is, Craig, this is a physics trick. The trick is that atmospheric pressure is pushing or pulling, but it's not.
Okay.
The reality is that what you can see right now, with the blue, cold, low pressure inside a container will pull the egg in. There's no other way for that egg to go in that.
Yes.
There's no other way. Pressure.
It's being pushed by the atmosphere on the outside. Yes, it's being pushed by the. Yes, it is.
It won't happen without the low temperature.
But here, okay. But listen to what I'm saying. But hey, listen to what I'm saying though for a second. When you lower the pressure on the inside, okay, you're not creating a sucking force. You're creating a pressure differential. All right.
That is a
no.
vacuum.
How do you? Yeah. No, it's not a suction force. That's the problem. You're not understanding it from the way it is. Like if you go underwater, does it matter? Let's say you go 10 meters underwater and you feel pressure on your ear, okay? Does it matter which way you turn in the water for the pressure to affect your ear? Like does it affect you more if you turn? But hold on one second. Hold on one second. But hold on. No, because they both press out in all directions equally. Okay, so it's not really different. So when you're when you're down 10 meters deep and you turn your head, but Spurs, hold on, hear me out. When you turn your head, you're not going to feel any difference. Like it's not going to be different if you hold your head up than you hold your head sideways because the pressure is coming from all directions, up, down, left, right. Same thing with the air. So even when you turn that plate on the sideways, even when you just have it here and you remove the pressure on the inside, there's still pressure trying to push that egg down in there because it's pushing down, just like there's pressures pushing on the side of the bottle.
No, that's your belief. You haven't proved it. Craig, there's one more clip, please. There's a little with the egg. So just after the egg. So just look in the thumbnail for the egg one, and then there's a clip just after. No. The egg cooking on the ground, if you remember that one.
Yeah, which is...
I think that's no, back. Oh, I can't remember where it is. It's. So I'm going to show again that a vacuum is created in all kinds of situations. Yeah, there's the egg. So go after.
I know how to fix this problem.
So look here, the boy. So pause. You can pause. Yeah, pause this. Yeah. So we can see that the low temperatures.
This is from a movie.
Pulling his tongue. Yeah, but again, let's look at the science behind here. What's happening to his tongue? He's pulling one way, and well, you explain to me then.
The water, the moisture on his tongue is turning into ice, and it's bonding with his tongue and the pole at the same time. Okay, and what does this prove?
But it's pulling his tongue.
It's not pulling. No, it's not pulling. It's not pulling. It's just attached to him. It's bonded to it.
He's not pulling. There's no pulling here.
Well, I imagine the little boy's trying to pull his face off of that.
Yeah, the kid's pulling, but
so as he's pulling precisely as he's pulling as his tongue is pulling, the other side is pulling back. That's the point.
Well, I mean, yeah, you could say that.
You could say that. You are correct.
Yeah, you're right. I'm not. Okay, I see what you're. Now that you want to talk science, but we're going to hold you to that science. If you're going to start quoting physics, we're about to start quoting physics.
Yeah.
No, this is real.
But you just denied physics. No, but you just denied physics a moment ago when we told you that it's the atmosphere from the outside pushing in. That's what science says.
Ask yourself here, what's going on here? Is what his tongue is against is pulling his tongue. Won't release it. It's pulling it back. It's not pushing, otherwise it'd let it go. And that's what happens in a vacuum in the low temperatures. They pull. The same thing with the candle. It's the same thing here. Exactly the same thing here. Low temperature.
Spurs, you do realize that if that kid just got close enough to that pole, it would suck him to it, according to you?
No.
He doesn't have to touch it. He just needs to get pretty fucking close. No, that's all he has to do is get pretty fucking close.
High temperatures release him. If you play the video, look how he gets released. There's only one way to release, and that's either the temperature around him.
Yeah, melt the ice.
Yeah, temperature. He has to have a warmer temperature around. And again, here, look here.
Yeah, you have to add energy to those bonds. Yeah, you're right. You have to add energy to the bonds and change them into a different state of matter. Yeah, you're right. Okay.
Look, 30,000 feet. nose, you breathe in through your nose and out through the mouth, right? So he's breathing in all of this pressure that's supposed to be dropping, and there's a big hole in the window, right? How is this possible? And all the other passengers are just like what he's doing, not wearing their masks correctly, right? So again, there's no pressure drop.
You realize that there's still oxygen there. It's just there's a much lower pressure.
Oh yeah, you can make excuses now, but there's no pressure drop. We can see that.
If there's no pressure drop, then why does all the air in the plane rush to leave the fucking big hole?
Because the temperature's trying to equalize, and it's moving.
Which means there's a change in pressure.
Even when you drive your car, you open your window. So when you open your window on a hot day, it's still hot. That's the point. You're still breathing. It's still blowing in hot air, right? So it's just the air is just trying to equalize. Many different examples. When the body is hot, it's too hot, you need to go into a cold bath to equalize the temperature. You know, otherwise you'll sweat to death. You go in a sauna, the temperature is high, so that the reverse, not low temperature, but high temperature. Simple science. I don't understand how people are not getting this.
No, that's the thing, Spurs. We get it. We really get it.
Yeah.
But we're trying to explain it to you. But honestly, I think I had more luck explaining algebra to my cat.
Probably, but I would like to see.
Hey Spurs, let me ask you a question. Let me ask you a question, and I'm going to ask you what your interpretation of this would be. Okay, and I'm going to try to figure out a way of actually doing this. But if I could get the flame on the outside of that cup in another sealed container, and I could end up pulling the air out of the cup to equalize the pressure, would you believe that it's not the vacuum sucking, or would you still believe that it's the vacuum sucking? That would be. It's hard. I'm trying to explain. Trying to figure out. Yeah. You know what? How about this? I'm gonna set this up because I know what I'm trying to say, and since I don't have the ability to demonstrate it or show it right now, even conceptually show you, or maybe I can. Hold on. Let me get something set up. Y'all go ahead. I'm gonna open up Paint real quick, and I'll share that.
Because, like I said, I'm gonna have to dash quite soon, and you know it's been very nice and pleasant. I'm glad that you enjoyed the video at least. I may upload it to my channel.
I would seriously suggest uploading it to your channel because many globe earthers are going to want to respond to this.
Okay.
I know that you are now going to be episode 26 of Flerfs Are Idiots. And you are also going, obviously, the next subject of Team's Idiot video. I know Bob the Science Guy definitely...
Well, it probably won't be the next one. There's a... let me be honest with you. There's a few people in front of him that are well-deserving.
I'd rather you make it about the... not about me. It's not about me. It's about the information. And if the information is...
Hey, I always do. I always make it about the...
Look, you guys have to do what you have to do. But, I mean, the information that I put out there, I'm able to demonstrate. If it's wrong, then just put it right. But if you need to throw a few digs or whatever, but I understand it's understandable. You guys are going through trauma and whatnot, but that's fine.
I'll make it more fun. I'll make it more fun. I won't take it as serious as I do like Gigant or Mark Sargent.
Don't be gentle.
Don't be gentle. Spurs wants it. Spurs wants it.
You heard it. Hey, that's good. That's going to be the intro to my video right there. Don't be gentle, and then you're going to break the record. So.
I'll say no more. Okay.
Right, so...
all right, Spurs, man, you take it. Oh, well, are we closing it up now?
Yeah, I'm going to get off.
Are you leaving right now, Spurs, or are you hanging around?
I think Spurs
okay, yeah, that's what I thought. I didn't want
to...
Yeah, I'm getting off.
Okay.
All right, catch you
later. Spurs, thank you for joining, and I would like to get an invitation for when you receive your Nobel Prize. Is that possible?
No, because I'm not seeking any kind of fame or fortune. For me, the truth is the truth, and that should be told. And today is a historical moment because history will be rewritten. Because I can't see how you can demonstrate an actual pressure pressing on what exactly? What is it pressing on? We absorb. It's how we have tans. People get darker, lighter, because the atmosphere absorbs into whatever object. It doesn't push you away. You don't feel a squash like you do underwater. It's a completely different effect. So there is real-world pressure. There is real-world gas pressure, but only in a container. And like I said in the video, we do not live.
Well, hold on. I want to ask you that. I'll ask you that. Let's say you're on a train, okay, and a bunch of people pile into the train. All right, now you're standing shoulder to shoulder. You don't have a lot of room to move. You're not really bouncing off the walls, are you? I mean, the walls aren't really, the container of the train is not really doing anything to you, right?
Yes,
it's the people that are around you. You're bouncing off of them. So there's still pressure. Even though it's not pressing on the container, only portions of the atmosphere are pressing on it. Not atmosphere, but I'm talking about like if you have a if you have like a balloon, right? Only portions of the balloon are pushing off of the outside. Everything else is pushing off of the rest of the molecules inside of the balloon.
If I like your analogy, let's say you've got a mini, and you have 25 people in the mini, you can't fit another person in, can you?
Yeah, sure, you can.
That's the limit.
If the people are compressible, yes. If it's gas, yeah, then you could.
Right. That's the limit. So you can't overfill, overload, right? Otherwise it will explode. Yeah?
Well, no, but not with gas. With gas, it's different than water or liquids or solids. With gas, you can continue to put more in there, and it just presses harder and harder back out.
Have you never filled up your tire? And you can't just put as much pressure into your tire, can you? As much as you want.
Right, because it exceeds the force holding it together. Right. Okay. So you could theoretically, you could put in as much gas as possible until the pressure pushing out exceeds the pressure of the container holding it together.
Yeah, that's the point.
At that point, you just burst the container like the tire.
That's the point. That's what I'm saying with the train. So if you put more people in, it won't hold. And now, obviously, if you keep putting people in with people, they'll just get squashed. But then there'll still be a limit.
Right.
And,
but they're not touching the outside of the train.
No,
not all of them are touching the outside of the train.
No, but the point is here, in the reality, this is not happening. It's not.
We're squishing people for science, man.
The atmosphere.
Adam Warlock says people are compressible. Just ask any serial killer. Right. Anyway, look,
Spurs. We can carry this on next time, Spurs. We'll carry this on next time, man. I appreciate you coming on.
Thank you for joining, Spurs. I know you you don't like to do it too late. I do appreciate you joining me at this late hour.
Yeah.
And thank you for that video. It's going to provide hours of entertainment for everyone that likes to debunk the flat Earth.
All right. Take care.
Catch you later. Oh, team. Always love having Spurs on. It's always interesting, eh?
Yeah, I just couldn't let that candle thing slide because it's just so completely incorrect, and they just don't understand it. I mean, you ask them, well, okay, so you tell them atmospheric pressure is 14.7, right?
Yeah.
You see, let's say you can create a vacuum inside of something else at 5.7 psi. It's going to equalize, right? And you're going to say, oh, the 5.7 is a vacuum. Well, now flip it around. What if you have a 14.7 and then a 28.7 psi? Well, now your 14.7, which was not a vacuum in the last experiment, now is a vacuum now. So it's not a matter of a certain amount of psi turns it into a vacuum. It becomes a vacuum due to its the relative psi, the relative pressures. And anything that's at a lower relative pressure is going to be considered a vacuum to a higher pressure. And that's just the way it is.
I know. That's why I tried to explain to him the fact that we know it's not a sucking force because there is a limit to, no vacuum is stronger than the atmospheric pressure because that's what that's what a vacuum is. It's allowing the atmospheric pressure to push into it. So, no matter how strong a vacuum is, it can't exceed what the atmospheric pressure is for what it needs to do.
That's what I probably should have. That's how I probably should have posed it to him and said, "Hey, look, if you think it's that the smaller pressure is pulling right, then you can't say that the 14.7 is pushing, or you have to say it's pulling too.
Yeah.
Because in the other example I gave, the 28.7 to the, or the 29.4, we'll say, just to make it even, 29.4 to 14.7, well, the 14.7 all of a sudden becomes this pulling force instead of a pushing force?
Yeah.
Just because we ran the experiment with a different PSI as you know, the relative PSI that we were comparing the 14.7 to. So when we compare it to a 7.35, of course, the 7.35 is pulling and the 14.7 is pushing. And then you look over on the other end, it's like, oh no, well, the 14.7 is actually pulling. It's a vacuum as well, obviously.
Absolutely. Oh, man. Right, so I think we should round this up with maybe another edition of My Buddy's an Idiot. What do you reckon?
I am not in a position to do that right this second. Give me 1 second. No, because I don't have the chat or anything open up. So give me like, I guess we could start it, and I'll just catch up as soon as I get logged in. Hold on.
Yeah.
Go ahead
Guys,
and
get those
start
My
it.
Buddies and Idiots in. You should have a lot after Spurs, and we'll do some My Buddies and Idiot, and then we'll close out for tonight. That was a lot of fun, and I watched it earlier on Ranty's round table, and I kind of like what Ranty's doing with his thing, and I kind of want to go on to Ranty's channel and do a presentation of my own. Also, because it's a chance to interact with Nathan Oakley outside of Nathan Oakley's channel, which I'm never ever going on. So maybe I can get him into a debate on Ranty's channel. That would be fun. So guys, why is my buddy an idiot? Let's get those in the chat. Haven't seen any so far. Marcus Dresden says, my buddy is a fucking idiot because he is a flat earther. Yeah, I think that's all you need, really. Mike Eberhardt, my buddy's an idiot because he thinks fire makes things cold.
Sorry, I forgot to turn on live chat as on top chat. That's what I always keep forgetting to do. All right. Factard, my buddy's an idiot because heat now makes stuff go down. Heat made things rise.
Morton Nelson, my buddy's an idiot because he thinks cold things are hot.
Rider of Dinosaurs, what's up, my brother? I love your work, man. Everybody needs to
absolutely.
subscribe to Rider of Dinosaurs. He has amazing, from my Dumbfuck of the Year nominee, JM Truth, Rider of Dinosaurs is basically, he's my proxy lawyer. He's making my case for me right now.
Yeah,
Thank you very much, Rider. And in your honor, I'll read it. And he sent this to you, but I'm reading it. My buddy's an idiot because he debated FTFE and thought he was changing history. Yeah, no.
Cap Scar says, my buddy's an idiot because she wants to have Spurs' children. No, don't let Spurs breed.
Oh, gross. Gross. Hunter Guerink, my buddy's an idiot because he didn't buy quality dingers. Ow!
Oh.
No, I know. I'll get a quality dinger one day.
Diego Lorenco, my buddy's an idiot because he thinks he has made a huge change in science today. I know. Spurs changed what we know.
Dan Robinson, my buddy's an idiot because he never siphoned petrol from a tank.
I think he
meant tank, but I said tank. Yeah. Hey, I read it how I see it. This is Ron Burgundy style shit.
Caliban, my buddy's an idiot because he thinks that temperature sucks objects because of colder temperature. Yeah, man, my fridge sucks me in every time I open it.
I'm waiting for somebody to put in that that actual question mark at the end of one of these so I can just be like, the Athens 619, my buddy's an idiot before he doesn't know how a sextant works?
Brown 01, my buddy's an idiot because he thinks fire makes air colder. Yeah, there's a lot of that. Spurs thinks fire makes cold.
General E. Shady, my buddy's an idiot. He watches Neighbors.
Everybody needs good neighbors. I was more of a home and away guy. Hemlock, my buddy's an idiot because he can't suck it.
Malicious Bloke, my buddy's an idiot because he turned up to work today with odd shoes.
I've actually done that before. Stephen Steen, my buddy's an idiot because he thinks the world is a ball. Yes, Stephen, we're all idiots.
Darth Weezius, my buddy's an idiot, or my buddy's a fucking idiot because he thinks he just made history. No.
No, he didn't. And I think this will be the last one for now. Radical, the Unhallowed Knight. My buddy is not my buddy, but holy hell, he just assumed fire makes things cold. Yeah, Spurs
We
is
can't
a fucking
end it
idiot.
right there. We have...
Right. Oh my god, there's so many more. I didn't realize.
Yeah, well, no, we at least need to get Tau Ceti Alpha. Tau Ceti Alpha, my buddy's an idiot because he claimed that barometer and thermometer are the same. Yeah, Spurs, that was some pretty class A fucking shit you just said right there. And for that, you are a fucking idiot.
Ding. You know, if I hear someone say the word idiot now and it's not followed by a ding, I start to feel like agitated.
Yeah. Yeah, I've hit my child several times when I hear people say idiot with no ding. I'm like, bah! He's like, why'd you hit me? I'm like, dude.
All right, so I'll just read off the last.
No, I'm just kidding. Don't hit your children,
don't
people.
Hit your children. Unless they're flat earther. I mean, no, even then. Right, so, well, goodness me, there's quite a few. Right. Earth is seriously flat, another $2, thank you. No scientific evidence of spinning nor a curvaison. That wasn't, I couldn't read it, there wasn't enough super chat there. Earth is seriously flat, do some more. 199 from Jen Morgan. Spurky, X equals, yeah, no, he couldn't solve that, honestly. I don't think he understands algebra at all. $2 from Bearded Devil 1864. Spurskimo, why do hot air balloons rise? Because magic. €2 from the Snark. I've never seen you be so patient, Teen Skeptic. Yay. Hey, you held it together well there. £2 from Malicious Bloke. He is not a force. Are you a potato? $2 from Jeffrey Greyjack. Thank you. $5 from Logical Hillbilly. Since all the Spurs evidence is either cartoons or someone else doing something, then by his own rules, it's all inadmissible. $1.99 from Stephen Steen. It's pulling his tongue, you idiots. Oh, Stephen Steen. $5 Australian from Demonic Davros. Third law of thermodynamics makes his argument fall apart. Yes, but he doesn't know what thermodynamics is, so that makes no difference to him. And $50 from Aussie Globehead. Thank you very much. My dog's left nut is smarter than Skidmark. That is very insulting to your dog's left nut. I think you owe your dog's left nut an apology there, actually. £5 from Dan Robinson. I refer the Honourable Muppet to my earlier question on siphoning liquids. No, he can't answer questions. $2 from Justin James Homan. Do tanning beds change atmospheric pressure also? $14.99 Australian dollars from Stephen York. You can get the egg out of the bottle with your mouth around the rim and the egg seal in the neck. You simply blow into the bottle and lift. No heat required. Spurs, you're an anaerobic bacterium. That is a brilliant insult, and yeah, well done. Anaerobic bacterium. Spurs, that's what you are. $1.99 for Monochromatic Light Source. I've put the kettle in the fridge. $2 Australian dollars from Demonic Davros. What did he think rewrote history? His presentation, Davros. He thinks his presentation rewrote history. And one more from MA2 Fletcher Eisler. Thank you, sir. $5. Just Cause. That's a great game. I've played it loads. Yeah, team.
Oh wow, Adam Warlock has a really great comment. If your child is a flat earther, just don't vax him and go start over.
Yeah.
Oh yeah.
I was talking to my wife earlier about this whole Storm Area 51 thing, and she thinks the military wouldn't kill them.
Bullshit.
Yeah, man. I tried to explain that they're going to be like, no.
I'll let you know that now.
Yeah. So
anybody ever stood shotgun watch will be able to tell you what the rules are of engagement. So
yeah, but it does kind of beg the question: what if like 1 million turn up and try to storm it? Is there going to be enough bullets?
They'll do some. They'll probably use like sonic weapons or some shit just to try to disperse a crowd.
Yeah. Anyway, don't storm Area 51, guys. That's a really stupid thing to do. Yeah, so thank you very much to Spurskimo tonight for coming and presenting that thing, I guess. Thanks, team, for hopping on.
Thing.
Yeah. Thank you, everyone, very much for watching. I will be back on Saturday with a new video. Team, what you got coming up?
I have a video tomorrow coming out, a Gigantor Part 2. Return of Gigantor.
Oh my God.
Gigantor strikes again.
Yeah.
Yeah, it's already done. I'm just, but hey, let me give a real quick, all my patrons and all my channel members, tomorrow we'll be doing a couple of live hangouts, private hangouts, so be paying attention to your Patreon, your Discord, and your YouTube, whatever, when I make a post, your YouTube notifications, and we'll see you guys tomorrow.
Yeah, I've got new updates and everything.
Oh, Monday. Tell them about Monday.
Oh,
Monday,
yes.
at Simon Dan's channel.
Yeah, on Monday on Simon Dan's channel, it's going to be me and Conspiracy Cats versus Team Skeptic and MC Toon in a Apollo 11 quiz. So, yeah, I guess we get to beat the Americans again.
Well, I already told Conspiracy Cats having you as a partner is basically like making him a three-legged feline. But so he's gonna be working with a handicap to begin with just by having you as a teammate.
Well, I just hope you're better at answering questions about Apollo than you are at playing FIFA.
Fuck off. You have no idea.
Anyway, guys, thanks very much for
Blame that one
watching.
on Simon Dan.
Yeah, I'm going to be starting regular Patreon hangouts and stuff as well in the next few days. The whole page getting updated, as well as with information about Project Eratosthenes. So make sure you check out my channel and my Patreon page for information on that. Like I said, I'll be back on Saturday.
Hey,
with
quick shout out to MC Toon, who is actually in the chat right now, and I agree with him. You're going down, Craig.
No,
and not
no.
in the way you like to do it.
All right, guys, who's going to win in a debate about Apollo 11? Is it a debate, a quiz? Is it going to be Conspiracy Cats and me, Team UK, or is it going to be MC Toon, the worst rapper in the world, and Twinkie over here?
Put a 0 if you
skeptic.
think. Put 0 if you think England's going to win. Put 69 if you want America to win.
No.
If you think me and MC Toon have got it.
MC Toon says he's got an Apollo 11 colouring book. He's totally ready. Oh, damn, man. I didn't think about that.
Shit, I watched a video the other day. I'm good, too.
Yeah, man. I mean, we all know we didn't go to the moon, so what's there to have a quiz about? Yeah, so guys, make sure you check out Simon Dan's channel, because you should all be subscribed to him anyway, right? But thank you very much, everyone, for watching. Once again, it's been fantastic. And remember, stupidity is not a right. Fight the flag. Fight the flag. Fight the flag. Fight the flag.